Alright, hello my name is AC and I'm going to be doing a final review of kind of the more recent units. I'm sorry if this is too late for you, it's my bad. And even for period 7, I'm sorry if this is too late, but if you're really cramming, if you're really locked in, then you can watch this video. Alright, let's get started. Alright, so first is a chapter 11 review. So this chapter is mostly all about ratios of the area and the perimeter, I think. And basically the only thing that you really need to know for this one is that the ratios of areas that you just square the ratios of the proportional sides. So for example, in this problem, one perimeter of the equilateral triangle is 6 times the perimeter of the other. So you have to find the ratio of the larger one to the smaller one. So basically, if this side is x right here, so that's bad. So basically, if this side is x right here, then this side is going to be 6x, right? Because one perimeter, or like one side, that's a typo on me, like one side is 6 times the side of the other, right? Which means we square the ratios of the proportional sides, so it would be a larger one to a smaller one, so 6x over x, right? And because these x's can cancel out, it's just 6 over 1. Then you square this, and you get 36 over 1. That's the answer. That's basically all you really need to know for the section. It's just proportional sides. So that's really all you need to know. And then you're probably going to have some problems like this. So we have to find the area and the length of segment GM. Alright, so first thing, this is 9 and this is 12. I'm pretty sure this is a parallelogram, so opposite sides are congruent. So this is 9, which makes this a 9, 12, 15 triangle. Makes this 15, and makes this 15, of course. And so the area of this triangle first is just, there's one triangle here, 9, 12, 15, and another triangle here, another 9, 12, 15. Which means that you can just put this triangle up right here to kind of make a square, and basically what that means is just to find the area of this entire shape, you just need to multiply 9 times 12, which is 108. So we know the area is 108. And this is an important step for the next part of the process, finding the length of segment GM. Basically, it's base times height, right? So we already took 9, 9, and 12 as the base and height. But now GM can work as a height because if this is a right angle, it's an altitude, which means that if this segment right here is 15 and base times height is equal to the area, we already know what the base is and what the area is. So we say 15 times height is equal to 108, and the height is 108 over 15, whatever that is. I don't feel like simplifying. And then something for each problem I'm going to do, don't forget the units. That's the most important part. I'm just running on a trackpad right now, so I'm too lazy for that. Alright, and then for this one, I'm probably not going to solve it just because I don't feel like it. So if EF is 6, first thing you can do whenever you see that one entire side is labeled but it's split into 2 parts is that you can label it with variables. So we can say EH is equal to 6 and HF is 6 minus x. Something like this, right? And if we know this is 6, let's say this is root 61, whatever, and we can say this is 7. I don't think it matters too much. But basically what we're going to do here is we're going to create 2 equivalent equations. So we have GH here already. So what we can actually do is say something like x, I'll do this pointer. Say something like x squared plus gh squared is equal to 7 squared. Then we have 6 minus x squared plus gh squared is equal to root 61 squared, right? Because both of these are right angles, so we can actually use the Pythagorean theorem. And that's kind of how you go about solving this problem. I'm not going to solve it right now, but I do recommend just to pause this video and walk through this problem yourself. Okay, so once again, I'm just going to go through the beginning steps of this problem. So BD is 3, right? And CD is an altitude, so it's a right angle, and BC is equal to root 30. So we need to find CD, AD, AC, and the ratio of ADC to BDC. ADC to BDC. So this is all about the altitude on hypotenuse ratios. So first things first, you can solve for CD, probably the easiest one using the Pythagorean theorem. 3 squared plus CD squared is equal to root 30 squared, right? And then from here, you have the sides of all of these triangles. So it's a lot easier to solve for, like, let's say, what do we want? AD, right? So if this is AD, then we can say, like, this entire thing right here is X. Let's say this entire thing right here is X. Then we can say this is X minus 3. Alright, so basically we already have this smallest side of the largest triangle, and we're trying to find the largest side, but we have the smallest one already. So by this point we already have CD, right? So we can create a ratio of the side CD to the longest side of the smallest triangle is equal to the smallest side of the largest triangle, root 30, to the largest one, which is X. And from here we can create a proportion and solve. And then, yeah, everything else, you can use something similar to this. If you don't know altitude on hypotenuse, I think I have a video on it, or I have a video surrounding about it, mostly ratios, but yeah. And then this problem down here as well, I'm not going to solve it, but this is definitely a very helpful problem. It might be on the test, it might not. I'm actually not entirely too sure. I'm not going to solve it, but something you do want to know for this problem, for something like this, right? So the ratio of area ABC, so A is right here. So the ratio of ABC, this triangle number 1, to the ratio of BDEC. So this quadrilateral right here. What you can actually do for this is you can find the ratio of 1 to 3, with 3 being the entire triangle here, right? And 3 is actually a combination of 1 and 2, right? And then you can just subtract the area of triangle 1 from this, and you can get 1 to 2. That's how you approach this problem for questions like these. That's my only tip for this problem, and let's move on. Alright, so general problems, general view. These don't really have specific units, but they're really helpful to know. So I'm going to be going walk around problems, certain angles, sectors, and segments. So this is basically very typical walk around problem you're going to see. So I got really lazy, and I just pasted an image of a worksheet in here. I do recommend doing this just over again. If you've already done this, I recommend doing it over again. But 2 things you need to know right here. An inscribed angle will be half of the central angle's measurement. So for example, let's take this first problem here, 30A. Measurement of arc BD, this one right here. So we know B is a diameter, right? Because the center is at point C. And we already know this part is 130, so we already know BD is going to be 50. Okay, so after we find this, I'll probably come back to this later, but another important thing to know is this chord tangent thing, right? So the intercepting arc, this angle created by the chord and the tangent will be half of the chord. So for example, if we want to solve for angle BFH, so number 30G, so down here. If you want to solve for BFH, right, the arc that intersects the chord and the tangent is 80 degrees. So this right here, this angle will be 40 degrees because it's 80 over 2. It's that simple. And then, yeah, you can continue on with these problems. These are basically the only 2 you need to know. You do need to know more for this problem, actually, but I do have an entire chapter 10 review. I go over this in depth, and I do recommend watching this video if you don't know these. Alright, so this is definitely a common problem, and I am willing to bet money that this will be on the final. So Find the length of a common external tangent of two circles with radii 2 and 9 if their centers are 25 centimeters apart. So I'm going to walk through this problem just because it's pretty simple. So common external tangent is going to look something like this, right? And my tip for you for this problem, if you don't know by now, you have to create a parallel line. Do not create it parallel to this thing right here. Always make it parallel to this line right here. Always. So, you draw two radii, right? These are 90-degree angles. Always draw it parallel to that common external tangent. So we know the radius is 2 here. The radius will also be 2 here. This is a rectangle, right? They're parallel. And then which means this is 7. And from here, we know the centers are 25 centimeters apart. So we already know this one's 25, this outside external part. And if this is 7, this is 25. And we know this is a right angle as well. This will be 24. And because this is a rectangle, this will also be 24. And that's the common external tangent. And the only tip I really have for these questions is to just always make the line parallel to the common external tangent and not the line that is the distance between the two circles. Alright, so this is probably another common problem. We have to find the area of the shaded region. And my tip for this problem is to first find the area of this entire part, right, including the triangle. And this is really easy. As you can see here, it's actually a part of the circle, and if we know this is 120 degrees, it's 120 over 3/60ths of the entire circle, or 1/3. So we can find the area of the entire circle. We know the radius is 18, so it's 18 squared pi. Okay, so it's like 324 pi. You take 1/3 of this, right? And then what you do is you can find the area of this triangle. You find the area of the triangle and you subtract it from the area of the entire thing, which is 1/3 of 324 pi. You take 1/3 of 324 pi and you multiply it and you subtract the area of this entire triangle. And if in a case like 120, you just split this in half, this angle becomes 60, and it's a 30, 60, 90 triangle. Alright, this next problem, it's actually a walk around problem. If you look closely, these are tangents. And basically what this problem is asking for is, it's asking for the radius of this inscribed circle. So what we can do, basically we know all these are congruent. Basically we can just start in one place. Like for example, let's start here. We know both of these are x, which means that this side will be 8 minus x. So we know this is 8 minus x. And because this is 15, we know this is actually, this part right here will be 15 minus parentheses. Here, let me write it out. That part will be 15 minus 8 minus x. And multiplying this out, distributing, it's 15 minus 8 plus x. And this is just 7 plus x. So we know this is 7 plus x. Alright, we also know this is 7 plus x because they're congruent. Tangents from the same point are congruent. So if you know both these are 7 plus x, so we know 7 plus 2x, right, or 17, right? So we know 17 is equal to x plus 7 plus x, or 2x plus 7, which means x would. That's a miscalculation on my part. X is not 10, x is 5. So if you know x is 5 here, then we know that both of these are 3, right? Because 8 minus 5 is 3. And we can actually create a square here, right? And because this is a square, we know both of these are going to be 3. And both of these are the radii, so we know the radius is 3. That's how you approach a problem like this, if you ever see it. Alright, this next problem, it's good use of the power theorems. So, core power theorems, especially this one. So we have two chords, right? You can create two equations. You have this small circle right here, and you have this larger one right here. So you can just create two equations, right? So the smaller circle first, let's say. So 4 times x is equal to 3 times y, right? Quarter power theorem. And then you have this bigger one. So like 6 plus x times 4 plus 6 will equal to 5 plus 3 times y plus 5. And using these two equations, you can solve for x and y. I'm not going to solve it because I'm too lazy, but that's how you approach the problem. Alright, this next problem, so all 3 of these circles are tangent, and they're all inside of an equilateral triangle, and the radius of each circle is 2, and we need to find the perimeter of the equilateral triangle. So it's this problem is pretty similar to this one, in the fact that we need to use similar things. So first step, I say how I do it, right? If it's an equilateral triangle, we know each angle is going to be 60 degrees. So we can kind of create these triangles here, right? And for some reason, when you draw a line like this, it bisects it. I have no clue why, but you know, I got the problem right on the test, so don't question it. So we know this is 30, right? This is a 30, 60, 90 triangle. So it's a 60, and we know each radius is 2, right? So we know this is 2, which means this is 2 root 3, right? Makes no sense. And then we just solve for this middle part. This middle part is pretty easy. It's just 2 plus 2, which is 4. We already know this is 2 root 3, right? So we know one side of the equilateral triangle is going to be 4 root 3 plus 4. Alright, this problem is actually simpler than I thought. I'll solve it. So if you know each side is 4 root 3 plus 4, we can just multiply this by 3. Because it's an equilateral triangle, so we just multiply one side by 3. So it's 3 times 4 root 3 plus 4, which is 12 root 3. And then this final one, I'm not going to do any problems, but I am just going to review chapter 12. So chapter 12, it's all about surface area and volume of 3D shapes, basically. So the first one is the pyramid formula. So a pyramid is when all sides of the shape are a triangle, I think. Okay, eyeline. A pyramid is when it either has a square or a triangle base. So to find the volume is 1/3 times base times height, and the base in this case will be the area of the entire. It would be the area of the entire. Let me draw one out here. It'll be the area of the entire base, so it'll be the area of this entire part times the height, which extends down to the middle of the shape and creates right angles. That's going to be the height. You multiply the base times the height, and you take 1/3. You can kind of imagine it like the base times the height. You can imagine it in a triangle or a square, like Pringles can, kind of, and the pyramid perfectly fits in there. Like the base perfectly fits in there, and you just squish it down. It's going to be 1/3 of the height. And in terms of its surface area, you just solve for each side of the triangle. It's not that hard. For the cylinder, this is where it starts to get a little more complicated. So the surface area of the base of a cylinder will be pi r squared, right? Just the formula for a circle, which is what the base of a cylinder is. And its lateral face, so that the part that is usually the longest, is going to be 2 pi r times height. Now, do you notice something about this equation? Look, this 2 pi r, it's the circumference. So what you're doing with the surface area, the lateral face, is what you're doing is you're taking the circumference and you're just multiplying it down by the height. You can imagine it top down or bottom up even. I think bottom up will be more intuition like. So you just multiply bottom up. Like the same way that the volume is pi r squared times height, which is the entire area of the bottom base multiplied by the height. You have h stacks of the volume of the circle. The lateral face is very similar, in which you have h stacks of the outside perimeter fence of the circle, and that's where this equation comes from, 2 pi r times height. And then for a cone, the surface area of the base is pretty simple. The base is just here I drew a cylinder right here. The base is usually just a circle. The base is a circle, so it's just pi r squared. The lateral face is pi times r times l. So the radius is obviously the radius of the circle, right? And then r, or pi r, and then l, which is the lateral side, the lateral edge of the pyramid, or of the cone. Of the cone. And the volume is also 1/3 times base times height, in which the base is the area of the circle. Sphere, I don't know. I think you need calculus to. I'm pretty sure you need calculus to prove these, but for the surface area of a sphere, it's 4 times pi r squared, and then for the volume is 4/3 pi r cubed. Never forget this cubed as well. And then for a prism, there's a pretty lax definition for a prism. It's basically just literally, it's any shape that's extended upwards, or any shape that's extended like this. Like you could have obviously I'm drawing a rectangular prism. You could have a rectangular prism, you could have like a trapezoidal one. Like it's very lax on what you can have as a prism. Like you can literally pretty much have anything as a prism. But the number one way is, or not the number one way, but the way to solve for the volume is just base times height. And the base is very important. The base is the surface area of the base, obviously the area of the base. But the base is almost always the name of the shape. So in this case, the rectangular prism, that's maybe an ambiguous case because all of the sides are rectangles. Like for example, this trapezoidal prism, this shape I drew right here, this trapezoidal prism, the base will be the trapezoid, right? It's always in the name of the shape, almost always. So you can kind of think of it as the same concept as finding the as a cylinder formulas. Is you have a 2D shape, right? And all you're doing is just stretching it this way by the height. That's it. That's literally all you're doing. That's where that comes from. Obviously, the base is just the surface area of the base, so it'll be these shaded sides like this. And yeah, so yeah, that's it. If you're in period 7, good luck on the finals. Yeah, let me know what I should do with this channel after. Like, I don't know, should I go back and make more videos? You know, should I transfer my content to, like, you know, Trigon stuff? Yeah, just let me know. Alright, good luck on the finals. Have a good night. Or if you're cramming, like 20 minutes before, you know, good luck. Yeah, and I'll see you next video.